Good morning, class. We are looking at Calculus 1, Chapter 2, Review Limits and Derivatives. The first exam covers 2.1 to 2.8. Here's the second part, covering 2.4 to 2.6. The precise definition, continuity, limits at infinity, horizontal asymptotes. So what is the precise definition? When limit of f of x as x approaches 3 equals 5, it means f of x is close to 5 when x is close to 3. That's the concept, okay? The general writing class is in this format, and this is whatever epsilon larger than 0, there exists a delta larger than 0 such that if the absolute value of x minus a is less than delta, the absolute value of f of x minus l is less than epsilon. Let me do a little bit of it. Writing. So this symbol reads whatever in math. This symbol reads there exists. And this symbol line segment reads such that. Okay, so I'm going to read it one more time. Whatever the value of epsilon larger than 0, there exists delta larger than 0, such that if the absolute value of x minus a is less than delta, then the absolute value of f of x minus l is less than epsilon. Now remember, absolute value refers to distance. So within the distance of delta, okay, this is within the distance of epsilon. F of x and L have a distance of maximum epsilon. X and A have a maximum distance of delta. That's the concept. We can make the values of f of x within an arbitrary distance epsilon from 5 by restricting the values of x to be within a distance delta from 3, but x not equal to 3. In other words, if you expand the absolute value, okay, x is between 3 minus delta and 3 plus delta, x can't be equal to 3, then f of x is larger than 5 minus epsilon and less than 5 plus epsilon. When you work on the absolute value, I hope everybody remembers that if absolute value of x is less than, let's say, k, and k is positive, x is between minus k and k. Okay, assuming k is positive. K is some number. All right. So to continue, I need to clean up this mess. A precise definition of limits. Let f of x be a function defined on some open interval that contains a, except possibly at a itself. We say the function has a limit at a, and we read limit of f of x as x approaches a equals L. If for every small number, epsilon larger than 0, there is a number delta larger than 0, that's also a small number, such that if the absolute value of x minus a, that means the distance from x and a, is between 0 and delta, maximum value of delta, then the absolute value of f of x minus l is less than epsilon, meaning the following interesting mapping. So x is some value close to a, okay? Maximum can go a distance of delta. So a minus delta, a plus delta, somewhere in this vicinity. It maps to the y coordinate, which results in the limit. The limit is L within epsilon. So L plus epsilon, L minus epsilon, somewhere here. That's the concept. So in this case, for example, number 3, it's within delta. Then this is 3 minus delta, this is 3 plus delta. The limit is 5. That means within some epsilon value, a small value, 5 plus epsilon, 5 minus epsilon. So if you pick any number that is in this vicinity, then we end up with the y coordinate in this vicinity. That's the concept, everybody. All right. Let's look at this example. Example 10. Use the graph to find delta such that if the absolute value of x minus 3 is between 0 and delta, the absolute value of f of x minus 2 is less than 0.5. By the way, you can just read from the graph, but I want to show you the detailed solution in case you come across it and they want the detailed solution. And again, I'm reminding you of what I wrote. This is the synopsis of everything in the previous page. Whatever epsilon larger than 0, there is delta larger than 0, such that if absolute value of x minus a is less than delta, that results, therefore, absolute value of f of x minus l is less than epsilon. So guessing a value for delta given epsilon, which is a positive value, we need to find or guess the value of delta such that if this is the case, then this is the case. That's the concept. So we always start with this part. If we were to do it algebraically, I'm going to show you from the graph and we're going to look at it algebraically. So we start with this, which is this part. So we're going to write this. Absolute value of f of x minus 2 is less than 0.5. So we're going to write it here. Now again, remember what I said about the absolute value. If absolute value of x is less than k, where k is positive, this means x is sandwiched between negative and positive k. So therefore, this is sandwiched between negative and positive 0.5. We are going to move the negative 2 and add 2 to both sides. F of x is between 1.5 and 2.5, which is showing right here on the graph, okay? Now, what do we want to find? Delta. Again, this has got nothing to do with, just to find the delta, you really have to look at the graph. And you have to look at each distance, meaning this number from 3 and this number from 3.8. So let me just again erase. So we are looking at this. X is somewhere between 2.6 and 3.8. What should be this distance? Well, let's calculate this distance and this distance. To be on the safe side, you have to choose the smaller of the two. So take delta to be the minimum of these two values. These two values, this distance, 3 minus 2.6, and this distance, 3.8 minus 3. Now, this one is 0.4, this one is 0.8, and we choose the smaller of the two, 0.4. Any smaller number than 0.4 will do. X can't be equal to 3. Now, what happens if you don't choose the smaller of the two? If you go with 0.8, on this side, you're fine. See, within this distance, you're fine. But if you go 0.8 here, then you may end up somewhere here, which is not within 1.5 to 2.5. So for this question, I just wanted to show you this part, but basically you have to look at this part and make this decision. Example 11, we want to prove the limit of 4x minus 5 as x approaches 3 equals 7. And this is a precise definition, although remember, we just plug in. But I want to show you how this thing works, starting with the definition that I've given you up here. We're going to start writing this out. So the absolute value of x minus a, so everybody, what is a? 3. So x minus 3 less than delta. Then f of x, everybody, what is f of x? 4x minus 5 minus L, what is L? 7. So if x minus 3 is less than delta, therefore the absolute value of the function f of x 4x minus 5, 4x minus 5, minus the limit 7 is less than epsilon. So that's how we do the writing. And we always start with this part. Four x minus 5 minus 7 makes it 4x minus 12. And the idea is that to make this look like this or a multiple of that. So you start with the second part, absolute value of f of x minus n, and you make it a multiple of x minus 3 less than delta. And that gives you this guess because you need to find the relationship between epsilon and delta. So 4x minus 5 minus 7 is 4x minus 12. We can take the 4 out. And when you take the 4 out, it becomes identical to this one with the factor of 4 in front. So again, when you compare this one to this one, it's the same thing times 4. Or you can say, okay, if I divide this one by 4, it becomes identical to that. So we're going to divide by 4. Now, when you compare these two, okay, now we're going to compare these two. So the second part B, compare it. So put this one next to it. They are identical, so these two must be the same. So what is your choice for delta? Epsilon divided by 4. That's the main part. Now the proof is to show that this choice of delta works. Reverse steps. So we are going to go from here back to here. How do we do that? Well, we start writing this, and the choice for this is epsilon over 4. So if absolute value of x minus 3 between 0 and delta, or epsilon divided by 4, and I want to go back up there because this is divided by 4, I'm going to multiply both sides by 4. When I multiply both sides by 4, that 0 is not important, it remains at 0. So this is 4 sigma, this is epsilon. So divide, multiply both sides by 4. And let's distribute the 4 inside, we get 4x minus 12. And you know 4x minus 12 is the same as, so we are here. So we are going back. We are here. We can write this as 4x minus 5 minus 7. And that is the limit. 4x minus 5 minus 7 is less than epsilon. So this results in this. We're going to write this resulting in this. If absolute value of x minus 3 is less than delta, then it gives us the absolute value of 4x minus 5 minus 7 less than epsilon, and that shows the proof that the limit of 4x minus 5 as x approaches 3 equals 7. And if we were to go with the graph, we graph the function y equals 4x minus 5, and this is 3 within some delta, 3 minus delta, 3 plus delta. Delta is extremely small, and that puts us the answer within the epsilon of 7. 7 minus epsilon, 7 plus epsilon. Meaning, if you pick any number in between, you get the answer somewhere in between, within the epsilon of the functional value 7, which becomes the limit. So this is the precise way to prove that. And now we want to go with the concept of a continuity. The summary is that a function has a limit at a if the limit of f of x as x approaches a from the left is L and the limit of f of x as x approaches a from the right is a. In other words, the limit of f of x as x approaches a does exist. Direct substitution property for polynomials or rational functions. If the function exists at the value a, then the limit of the function as x approaches c is equal to the function's value at a. In other words, limit of f of x as x approaches a equals f of a. In short, every function that we have studied in pre-calculus, they are continuous in their domain as long as we know the domain of the function. For example, for polynomials, the domain would be all real numbers, okay? A function is continuous if the limit of f of x as x approaches a equals f of a. So continuity happens if the limit exists and it's equal to the functional value. So a function is continuous from the right if the limit of f of x as x approaches a from the right is f of a. And we say a function is continuous from the left if the limit of f of x as x approaches a from the left equals f of a. Here's the summary of the whole thing. And the IVT, short for the intermediate value theorem, says if f of x is a continuous function on the closed interval of a to b, so it has to be a closed interval, and the function has to be continuous. And let n be any number between f of a and f of b, the endpoints, where the two values are not equal. There must exist a number c in the interval of a to b such that f of c equals n. And this is used to find and prove that there is a root for a function, because normally they go with two values that one is negative, one is positive, and 0 is in between. Let's see what we mean by that. Let's start by looking at this simple example. Example number 12, determine C such that P of x is continuous at x equals 5. And remember, continuity has the following definition. The limit of f of x as x approaches a equals f of. Well, we want to take the limit of this function. This is a piecewise defined function, everybody. And because x is not equal to 5 here, we use this part at precisely 5 is this one. So let's take the limit of the function as x approaches 5 by looking at this. I hope you see that if you plug in, you get 0 over 0. Therefore, the technique is factoring. The technique is factoring. The top is x minus 5 times x plus 5. We drop the x minus 5. And now if you plug in 5, you get 10. So a function is continuous if the limit of f of x as x approaches a equals f of a, then it's continuous at a. So in order for this function to be continuous at x equals 5, the functional value must be the same. The functional value is given as c, therefore c must be 10. So the choice of 10 will take care of the business. Sure, the function is continuous on negative to positive infinity. And again, the definition of a continuity is that the limit of f of x as x approaches a equals f of a. So f of x is a piecewise defined function sine x if x is less than pi over 4 and cosine x if x is larger than or equal to pi over 4. I hope you remember, as far as the trigonometric functions sine and cosine are concerned, they are continuous everywhere in their entire domain of negative to positive infinity. Therefore, you have to check the end point, namely pi over 4. So each piece. So this is continuous from negative to positive infinity. Therefore, it's continuous from 0 to pi over 4. Same thing here. Therefore, it's continuous from pi over 4 to infinity. But what about pi over 4 itself? we have to check it out. So we know this is the case because this one is continuous here, this one is continuous here. But what happens at pi over 4? The end point, we must check. So the limit of this function as x approaches pi over 4 from the left uses this function. So the limit of f of x as x approaches pi over 4 from the left is the limit of sine x as x approaches pi over 4. Plug in, and sine of pi over 4 is square root of 2 over 2. We're going to look at the same thing, but from the right. And the limit of f of x as x approaches pi over 4 from the right, we'll use the second piece, cosine x. And you plug in, you get cosine of pi over 4, which is the same thing. So because the endpoint works, the limit of f of x as x approaches pi over 4 does exist. And it's equal to square root of 2 over 2. Also, f of pi over 4 uses which piece? The piece with the equality. So f of pi over 4 will use cosine. Why cosine? Because that's the one with the equality. So the limit exists, and it's equal to square root of 2 over 2. The functional value exists, and it's equal to the same thing. Therefore, the limit of f of x as x approaches pi over 4 equals f of pi over 4 equals square root of 2 over 2. That means the function is continuous at pi over 4. And therefore, it's continuous from negative to positive infinity, because pi over 4 was the only point we had to check. Use the RVT, the intermediate value theorem, to show that there is a root for this equation sine x equals x squared minus x in the interval of 2 to 3. So to refresh your memory about the intermediate value theorem, if the function is continuous on the closed interval of a to b, this function is continuous in the interval of 2 to 3. Okay, so we can bring it to one side and call it f of x. I'll explain why is this continuous. And then let n be any number between f of a and f of b, where the two values are not equal. There must exist a number c in a, b such that f of c equals a. Number one, we are going to look at some sort of a function by moving things around. So if I bring everything to the right or to the left, makes no difference, becomes 0. This is what we are looking at. So the function of interest, f of x, is x squared minus x minus sine x, and it's continuous function. Why is this continuous? Because it's a combination of a polynomial function of degree 2 and a trigonometric function. Combination of polynomial function and sine function, a trig function. The domain for any polynomial function is all real numbers, the same thing for sine, and therefore it's continuous from negative to positive infinity. Therefore, it's continuous from 2 to 3. We are going to look at a couple of values. We're going to look at the endpoints. For example, if you look at f of 1, okay, by inspection, we get 1 squared minus 1 minus sine 1. These two cancel each other. Negative sine 1 makes it negative. And if we plug in 2, that makes it positive. The reason why we plug in 2 squared minus 2 minus sine 2. As you know, this is 4. Minus 2 makes it 2 minus sine 2. As you know, sine can have a maximum value of positive or negative 1. So if maximum is 1, 2 minus 1 is positive. Okay. And since f of 1 is negative and f of 2 is positive, between 1 and 2, there must be a root. IVT applies. F of x is continuous. F of x is continuous on 2, 3 and has a root in between. Class, this is negative 2. And part 1 is some number in between. Okay, so just wanted to make sure you are okay with this. So a quick recap. We want to use the intermediate value theorem to show that there is a root for this equation sine x equals x squared minus x between negative 2 and 3. We bring it to the same side. Whether you take it to the left or right makes no difference. So we take it to the right, x squared minus x minus sine x equals 0. That is the same as saying this function, does it have a root? X-intercept. This is a combination of a polynomial and a sine function, so it's a continuous function from negative to positive infinity. Therefore, it makes it continuous from negative 2 to 3. So by inspection, if we pick a couple of points in between, we know f of 1 works out to be negative. We know f of 2 works out to be negative. So between 1 and 2, there is a root. Therefore, between negative and 2 and 3 must be at least one root. Okay. By IVT. Horizontal asymptotes, HA of the curve y equals f of x has the equation y equals L if the limit of f of x as x approaches minus infinity is L, or the limit of f of x as x approaches positive infinity is L. And so, for example, the limit of the function 1 over x as x approaches infinity is 0. And the limit of 1 over x to the power of p as x approaches infinity is 0 when p is larger than 0. For both of them, the line y equals 0, which makes it the x-axis, is the horizontal asymptote. So the concept of limit functions at infinity, let's look at y equals b to the power of x when b is larger than 0. When the base is larger than 1, okay, is an exponential growth. When it's between 0 and 1, it's an exponential decay. And example of this would be e to the power of x. As you can see, the limit of e to the power of x as x approaches minus infinity is 0. So y equals 0 is the horizontal asymptote. And of course, the limit of f of x as x approaches positive infinity is infinity. It blows up to infinity. In this case, the limit of e to the power minus x as x approaches infinity is 0. So y equals 0 works out for this one also. This is an exponential decay. And of course, the limit of f of x as x approaches minus infinity is infinity. So the concept of limits of functions at infinity. By the way, b is between 0 and 1. Please understand this is the same as writing 1 over e to the power of x, where 1 over e is between 0 and 1. Everybody is familiar with the graph of y equals x squared. The limit of f of x as x approaches minus infinity is minus infinity. That means the third quadrant. And the limit of f of x as x approaches infinity is infinity. This is known as the end behavior of the function. I hope you remember that. This was known as the end behavior. Okay. Vertical asymptotes. The definition was that the limit of f of x when x approaches a, or a from the right, a from the left, or a from the right, if it results in negative or positive infinity, we have a VA, vertical asymptote, with the equation x equals a. For example, you're all familiar with the graph of y equals ln x. As you can see, the limit of ln x as x approaches 0 from the right is negative infinity, and according to this, the y-axis becomes the vertical asymptote, and it has the equation x equals 0. So vertical asymptotes, or VA, of the curve is x equals a, as long as one of this is true. That's the synopsis of that. In this case, we are dealing with tan inverse. The limit of tan inverse of x as x approaches minus infinity is minus pi over 2, and the limit of tan inverse of x as x approaches infinity is pi over 2. This is the tan inverse, and again, you probably remember y equals tan x looks like this. It looks almost like y equals x cubed, and of course these are the vertical asymptote, x equals minus pi over 2 and x equals pi over 2. All right, we want to find the limits algebraically. Anytime the variable txy makes no difference is approaching infinity, you're dealing with a rational function. First of all, if you plug in, you get infinity over infinity. The technique is to divide by highest degree term in the denominator, which is t squared. By the way, to find the limit in general, just plug in. And if it gives you a number, you're done. If it gives you 0 over a number, you're done because it's 0. If it gives you a number over 0, you have to figure out it's positive or negative infinity. And many times it gives you 0 over 0, infinity over infinity, infinity minus infinity, and all of them are considered indeterminate. So for a question such as this one, you divide by highest degree term in the denominator, namely t squared. And you simplify. This becomes 5 over t, 7 over t squared, 1, 2 over t, minus 1 over t squared. And when you plug in, because the denominator is infinity, this is 0, 0, 0, 0. Everything is 0 except 1. And because the answer is 0 over 1, 0 over some number other than 0, the answer is 0. because t is approaching infinity, we are dealing with a rational expression. We divide by highest degree term in the denominator, namely t. And we simplify. This is what we get. If we plug in everybody, this becomes infinity. This is 2, this is 0, this is -5, this is 0. So the numerator is infinity plus 2, the denominator is -5. What I want you to pay attention to is the sign. The top is infinity, whether you have infinity plus 2, plus 10, or divided by 10, or times 10,000. It's infinity. The bottom is negative, so the result is negative infinity. It doesn't matter, it's -5 or -5 billion, okay? So when we divide it by -5, it changes the sign to negative. What about this case? We end up with 0 over 0 if we plug in. My apologies. We end up with infinity minus infinity when we plug in. It's one of those indeterminate forms, so we got to multiply by the conjugate and divide by it. This expression equals 1 and it's acceptable. So you keep the denominator and you multiply the top as follows. So let me actually erase something. So when you extend that, you multiply these two, you're multiplying a minus b times a plus b. The answer is a squared minus b squared, which means square the first one, which comes out, minus square the second one, which becomes minus x squared by the x squared. This is x. And so these two cancel each other, everybody. And now if I plug in infinity, then the denominator is infinity plus infinity, and the answer is 0. Now it's important to understand, class, when we come across infinity minus infinity. So let me just again clean up the mess and write down. Let's see. This expression would become infinity minus infinity. When you work out infinity minus infinity, anything can happen. It can become infinity, it can become 0, it can become some other number. You'll see it as we look at more examples. We want to do this, and we simply plug in infinity. I hope you know if you plug in infinity, e to the power of minus t becomes 0. And 12 over 4 is 3. And here's the reason, class. A to the power of minus m is 1 over a to the power of m. And therefore, e to the power of minus t is 1 over e to the power of t. So if you replace the t with infinity, that's what you get. In this case, although it's not a rational expression, the reason it's not irrational because rational means the top and the bottom both must be polynomials, and they are not. But you treat it as such, and since t is approaching infinity, you divide by highest value in the denominator, namely e to the power of t. When you do that, this remains, this becomes 1, this remains, this becomes -3. Since t goes to infinity, so does e to the power of t. This goes to 0, this because 5 is divided by infinity. This goes to 0, positive 1 over -3 gives us -1/3 as the final answer. Limit of x squared minus x as x approaches infinity. If you plug in, you get infinity minus infinity. It's an indeterminate form. So what is the technique? Factor the x out. When you factor the x out, now you plug in, you get infinity times infinity minus 1, which is, of course, infinity. Infinity times infinity, infinity times 2, infinity squared, square root of infinity, all of them are infinity. By the way, if you plug in, you get infinity over negative infinity. But the technique is x is approaching infinity, so we divide by highest degree term in the denominator, namely x. Divide everything by x, everybody. When we do that, this becomes x, this becomes 1, this is 3 over x, this is minus 1. And now if we plug in, we get infinity plus 1 over 0 minus 1. So the top is infinity, plus 1 or plus 10,000 or minus 10,000. The bottom is negative 1. So the result is negative infinity. So you want to be very careful with the sign, everybody. The answer is negative infinity. All right. The limit of e to the power minus x plus 2 cosine 3x as x approaches infinity, we are going to use the limit laws and we cut it into 2 pieces. This one does not exist. Why is that? First and foremost, please understand this is 0 because it's e to the power minus infinity, which is 1 over e to the power of infinity, which is 0. So this part is 0. But what happens here, this oscillates between negative 1 and 1. The limit of sine or cosine of x or 3x or 10x, when x goes to infinity, this one does not exist because it oscillates, okay, between negative 1 and 1. And therefore, the limit does not exist. It oscillates. It jumps up and down between negative 1 and positive 1 as x goes to infinity. To find this limit, although it is not a rational function, because x is approaching infinity and you're dealing with a fractional format, you divide by highest value in the denominator. So divide everything by e to the power of 3x. Now, as you know, when we divide this one by this, you get 1, this one by this, you get 1. I want to discuss this one. I want to make sure you understand what happens here. For this one and this one, we get e to the power minus 6x. I want to show you quickly why. So this one minus e to the power of minus 3x over e to the power of 3x. We use a to the power of m over a to the power of n is a to the power of m minus nd. Quotient rule. So it's minus e to the power of minus 3x, and it gives you minus e to the power of minus 6x. So I hope everybody is clear on that. Now, if you plug in infinity, then we get 1 minus 0 over 1 plus 0 or 1, because this expression goes to 0. The reason why, because e to the power minus 6 times infinity is e to the power minus infinity, and that is 0. We have shown it previously. The limit of tan inverse of ln x as x approaches 0 from the right. You should know the answer, but just to make sure you know what's happening, I'm going to show you a couple of graphs that is helpful for memory, starting with the natural log. So this is tan inverse of the limit of ln x as x approaches from 0 from the right. So because it's a continuous function, you can put the limit inside because the limit pertains to x. Now let's talk about ln x. Here's a graph of ln x. And what is this one? We have already done that it's negative infinity. Tan inverse of negative infinity. Now the question is, what is tan inverse of negative infinity? I'm going to show you two things. First, I'm going to show you the following graph. Again, reminding you of y equals tan x. Graph looks like that. And here's the graph of tan inverse. The graph looks like that. And tan inverse of negative infinity goes to minus negative infinity takes you to minus power 2. Another way of approaching this would be to say, what is tan inverse of negative infinity? How about alpha, beta, gamma? By definition of an inverse function, tan of alpha is minus infinity. So what is alpha? Negative power 2. Either way, so you can use the concept of an inverse function to come up with the answer. I hope both concepts are understood. Okay. Here's another limit we want to look at, the limit of sine squared over x squared plus 1 as x approaches infinity. And we're going to use the squeeze theorem. I'll refresh your memory about the squeeze theorem. G is squeezed between f and h. We're going to look at f and h, and whatever we get works out for g of x as far as the limit is concerned. And therefore, what we are going to do here, we're going to start with a known fact. Sine is between negative 1 and 1. We know that. We want to make it look like this. So if we square that, it's important when you square this, it's not going to be that you square this one and you get 1. Remember, if sine is between 0 and 1, when you square it is between 0 and 1. So it doesn't change the fact that there is a portion of it between 0 and 1. So whether it's between negative 1 and 0 or 0 and 1, when you square it, it will remain between 0 and 1. Let's say it was 0 and 2, would be 0 and 4. Between negative 2 and 0, then again from 0 to 4, because this does get squared up. Now we want to make it look like this. So far, so good. What is missing? This denominator. So let's multiply by 1 over x squared plus 1. And remember, this expression is positive. Why is it positive? Because the numerator is positive. X squared plus 1 is larger than or equal to 1, because worst case scenario, if x is 0, this is still 1. So because it's positive, it doesn't change the sign. It remains unchanged. So 0 times that is 0, the right side, and so forth. And now we're going to take the limit of the left side. That means 0 as x approaches infinity, which is 0. And the right side, which is also the same thing, 0. So the limit of this is 0. The limit of this part is 0. So the limit of the one in between by the squeeze theorem as x approaches infinity must be 0. And it is important that you write by the squeeze theorem. We're going to find the asymptotes, starting with the horizontal asymptotes. We take a limit of this function as x approaches plus minus infinity. And because it's approaching infinity, the technique is to class, whether positive or negative infinity doesn't matter. The technique is to divide by x squared, the highest degree variable in the denominator. So we divide everything by x squared. This is what we get. When x approaches infinity or negative infinity, makes no difference. This goes to 0, this goes to 0, this goes to 0, you end up with 2/3. And what does it mean? Horizontal asymptote has the equation y equals 2/3. What about vertical asymptotes? In order to get to the vertical asymptotes, all you have to do is set the denominator equal to 0 and factor it. Because 3 is a prime number, it's very easy factoring x and 3x in any order. And -1, it's 1 and -1. Just put them so that the middle term minus x and plus 3x, they add up to 2x. So this gives us x equals 1/3. This gives us x equals -1. So the vertical asymptotes have the equation x equals 1/3 and x equals -1. Find a formula for a function that has vertical asymptote x equals 1 and x equals 3. Horizontal asymptote y equals 1. So let's work on this solution and some possibility on that. So one possibility is that because the vertical asymptotes are x equals 1 and x equals 3, this can give us x minus 1. This can give us x minus 3. So this gives us x minus 1. And this gives us x minus 3 in the denominator. Now, as you can see, the denominator is x squared. And the rest is not important. But the first term, the leading term, is important. Because y equals 1 represents a horizontal asymptote, then the degree of the numerator must be the same. That means degree 2. And the leading coefficient must be 1, so we should have x squared. Now, the reason we say one possibility, I could say x squared plus 5. X squared minus 1 in the numerator. Makes no difference, it gives you the same answer. So that's it for today.